What's up?
Yo, it's good.
Nothing much. Just how are you doing?
I'm chilling. I'm chilling. It's been a long day,
Yeah.
almost over. I'm gonna go to the basketball game after this. So
Oh, there's a basketball game right now?
yeah, it's non-conference, but it it's at 7. So
Oh shoot. Nice. Yeah, today should be pretty short. So compared to
I'm
our
doing was it chemistry and physics?
yeah.
Gotcha. Okay. Perfect, because that's or chemistry at least is what I need the most focus on.
Oh, all right. Yeah.
Yeah. I haven't taken a gen chem since like high school. So
Yeah.
it's been a very, very long time. So definitely need to brush up on those topics.
Yeah. That makes sense. It's, Hema. Let's see. Do you know if Chris Shaw is coming today?
I'm not totally positive because he just had a biochem exam today. So
Oh, let's see.
yeah, I'm not sure how much of his brain is still working.
Yeah.
He should come. I don't know why he wouldn't, but
Yeah. It's Andy. We'll wait for a few minutes for other people to show up and then we'll get started.
sounds good.
There it is. What's up, Rishal?
What's up, Ted? How are you?
Doing good. How are you?
Okay.
What's this one here?
How you doing?
I'm doing good. How are you?
Pretty good.
Right. Is Cam busy again, or is she?
Yeah, she's busy. She's doing some schoolwork.
Yeah, that makes sense. All right, I guess you can go ahead and get started. Okay. Let's see, can everyone see the screen? Good. All right. So today we're going to be looking at a few passages from the chemistry and physics section of the MCAT. So these are like a bit on the easier side, I would say. So they're somewhat simple. Well, I wouldn't say simple, but I would say like easier compared to other passages, I would say, but it's a good review and like brush up of some of the concepts. So before that, if we could start with an icebreaker. So if like you go around, say your name, school, and then like who's your favorite musical artist?
I can go first. So my name is Momin. I go to VCU, and my favorite artist is probably Lil Uzi.
That's fire.
My name is Samir. I go to VCU, and I would say my favorite artist is probably this guy named Xavier Wolf.
Oh shoot.
Xavier
Never heard of that. What genre is he?
Rap. He's
Oh,
fun.
rap? Dang.
My name is Kushal. I go to VCU, and for me, it's probably either like it's like a toss up between J. Cole and Kanye for me.
Dang. Yeah. I'm a fan of both, I would say.
Hi, my name is Rishi. I go to VCU, and my favorite musical artist is Ice Spice.
Ice Spice. That's funny. All right.
I can go. My name is
Yeah.
Andy. I go to VCU, and just based off my Spotify like numbers,
Mhm.
I listen to a lot of Khalid.
Oh, nice. So it looks like we got like a good amount of variety. All right. Well, I guess we can go into the actual lesson now. So you've probably seen this before, but this is like a pretty common physics problem where like we have a block on an incline. So to get us started, let's like start drawing some forces that could be acting on the block. So can anyone tell me like what forces could be acting on the block and what direction that could be acting?
So we would have normal force acting on the block. So
Mhm.
like at like a diagonal. And
So what would that
like
look
like it's just straight off the block.
like? Yeah.
Yeah.
So like this, right?
Yeah.
Awesome. So we can call this a normal force. What else could be acting on the block?
Gravity
Gravity. Yeah,
acting directly down.
exactly. Just call
Can
this.
y'all see the forces?
Oh, you can't see them?
Yeah, it's not, I don't think it's drawing.
Shoot. Wait. Oh, I hold on a second. Yes. Okay, do you see them now?
Yes, we can.
All right. Awesome. Awesome. And so gravity acts straight down, right? But like, what are the components of gravity? Like what's actually acting directly on the block? Like what directions? Like
Like friction.
yeah. So we forgot friction. So friction would be acting this way actually. So I'll call this just F. So normal force is it perpendicular or is it parallel?
perpendicular.
Right. And then is friction parallel or perpendicular?
Be parallel, right?
Right. So let's draw our, so this is our perpendicular component of gravity. And this is our parallel component. Okay. And so the block is at an incline of an angle theta, right? So what is this angle right here? This blue line and the triangle. What is that? So it's just a right triangle. So what would this be?
90 degrees.
Yeah, 90 degrees. Okay. So this angle right here. So see right here. This will be 90 minus theta, right? Because we have 90 degrees here. And we know this plus this has to be 90. Okay, so this is 90 minus theta. But then this thing right here, this blue line, it also makes a 90-degree angle with the triangle. So we know this is 90 minus theta. So this must be theta, right? So that's just kind of how we figure out that this angle here is also theta. Okay. So we know gravity is always equal to mass times the gravitational constant, which for the MCAT is usually just 10. All right. So we want to figure out what the components are. Like, how do we get the perpendicular component of gravity?
Mg sine theta.
Mg sine or mg? So okay, so cosine is horizontal. So yeah. So think of this as like horizontal and this is vertical. All right. So imagine you're starting here, right? This is you're going out from the center of the circle to the outside. So this is the horizontal part actually. And this is the vertical part. So what do you use for vertical and what do you use for horizontal? So
Horizontal, you use a cosine, right? And
Right.
vertical, you use sine.
right. So you do the magnitude of your vector. So this is your main thing right here, weight, right? And this is just mg, right? So if we want to get our horizontal part, or in other words, our perpendicular part in this case, what do we do? How do we figure that out?
Mg cosine theta.
Exactly. Mg cos theta. Awesome. And then what would our parallel component be?
It would be mg sine theta.
Awesome. Mg sine. Awesome. So it looks like we have all our forces there. So for a block that's sliding, what is the normal force going to be equal to? If assuming it's just sliding down the ramp.
Mg cosine theta.
Exactly. Because it's not going to be accelerating perpendicularly, right? It's just right. And then, but what is going to be the net force on the block when it's sliding down the ramp? Like parallel.
Mg sine theta minus the kinetic friction. I mean,
Exactly.
kinetic.
Right. Okay. So that is all I wanted to really get from that. So yeah, so this is the same thing we had before. Does anyone have any questions about this diagram? Awesome. Okay. So basically, can someone just define what friction is? Just real simply.
Force that opposes motion.
Exactly. So what are the two types of friction?
Kinetic and
and
kinetic friction.
Yeah, exactly. All right, so basically what happens with friction is when you have an object, for example, on a ramp, the object stays still all the way up until a certain point. So friction builds all the way up until you reach a peak. But there's a point where friction can't keep the object still anymore. For example, the force on it may be so big that it starts to move. But you're still going to have friction even when an object is moving, right? If you like slide a block and it's moving, it's still going to stop eventually at some point due to friction, right? So at the point where the block starts moving, your friction drops down to kinetic friction. So the max friction is which type of friction? Just based on the graph here, what would be the max type of friction?
Would it be static?
Exactly, right. So how you tell whether it's static or kinetic friction is if there's movement at the point of contact between the object and the surface. So a block sliding on a table, what type of friction is that?
Kinetic.
Kinetic, exactly, because the block is sliding past the surface, like they're moving relative to one another. All right. And so the formula you use to calculate friction really depends on what type of friction it is. So the force of friction is equal to the coefficient of friction times your normal force. So what is our normal force equal to again, like in the block example? Does anyone remember?
It's would it be the horizontal component of weight?
Right. Yeah. So it would be, well, we would say perpendicular, but like, yeah, the same thing. So the perpendicular component of weight, which is what value was that?
mg cosine theta.
Mg cosine theta, exactly. So it would be your coefficient of friction, assuming it's sliding, you would use the kinetic coefficient, right? And you would multiply that by mg cosine theta, and that would give you your frictional force. All right. Anyone have any questions? All right. So there's another type of friction called rolling friction. So when you like, for example, push a shopping cart, you have wheels that roll on the ground, okay? The exception here is that there is no movement at the point of contact between the wheel and the ground, okay? So we define static friction as when there is no movement between the object and the surface, right? And we define kinetic friction as when there is movement between the object and the surface. So if I tell you at the point of contact between the wheel and the ground, there's no actual movement between the wheel and the ground, like there's no relative motion to one another, what type of friction is that?
Static.
Static friction, exactly. So you want to make sure you pay attention. So like it can be a bit confusing because technically the wheels are moving, but at the point of contact, there's no movement between the wheel and the surface. Okay, so just keep that in mind. Awesome. Okay, so that's it for, so I said like today is pretty short, so that's it for the physics part. So now chemistry part, this should be pretty simple as well. So this is a typical rate of a reaction graph. So it tells you like the concentration of the species in your reaction over time. So you can assume the reactant concentration is going to decrease over time, right? And then you're going to get more products over time, right? That makes sense. Right. Okay, so that's pretty basic. So here we have an example of like just a random reaction that I made up. So x plus 2y forms a plus 2b. So on our y-axis, we want to know how we're measuring the rate of the reaction. So the rate at which the product is formed, aka the rate at which A is formed. So you want to look at the product which has a coefficient of 1. That's how you measure your rate of reaction. You don't measure it by 2b. So you measure it based on the amount of A that you form over time. So the amount of A over time can be expressed as delta A over T, right? Change in A over time is the reaction rate. And we can use a bunch of other terms to describe this in the same way. So what is the relationship between A and B? Like, what's the stoichiometry there? Just like the products, what's the stoichiometry between the products? Like, what's the relationship between A and B?
A
Two.
equals 1/2 B.
Exactly. So since A is 1/2 B over time, so remember we're measuring the rate of formation of A as our reaction rate, right? And we know A is always going to be, we're always going to have half as much A as we do B. So if we do 1/2 times the change in B over time, that's the same thing as a change in A over time. All right, that's the same reaction rate. Or because for every time you consume a reactant, you make a product. So the change in the formation of the product is the same as the change in the consumption of the reactant. So negative change in X over time is the same as the change in A over time, because every time we make A, we use up X. Okay. And same thing here, because so what's the relationship between X and Y again? Same thing.
X is 1/2 Y, right?
Exactly. So we're going to use half as much Y for our reaction rate, because the stoichiometry is 2-to-1. We're using if you look at the amount of Y, we're consuming half of that, and that's our reaction rate. All right. So does anyone have any questions about that part of the slide? It's awesome. So now that we know the rate of reaction, so rate of reaction is called R. So R for rate. So rate is equal to a rate constant times the concentrations of your reactants. And so based on the coefficient of your reactants, that's what you raise your reactant concentrations to in the rate law. All right. So can someone tell me what the rate law is? Okay, so a rate law is basically, so it's the rate of a reaction. So R. So what is K? Can someone tell me what K is? It says on the picture too. So.
K is the rate constant.
Right. And so these brackets around A and B, what do they represent?
Concentration.
Right. So we have a rate constant times concentration. So what is the rate of the reaction proportional to?
The concentration of the compounds.
Exactly. So, okay, so we got that. Awesome. Now last part. So remember how we said we have a rate constant in the rate law? Well, how do we know how to calculate that rate constant? We actually use this thing called an Arrhenius equation. So the Arrhenius equation has like an Arrhenius constant, and it has an exponent function. And the important thing to know is that, so E is raised to the negative activation energy over RT. So EA is activation energy. So you're raising E to the negative power. So when you raise something to the negative power, what does that mean?
exponential decay.
Right. So you have 1 over E. So if you're raising, so if you have 1 over E raised to the activation energy, if you increase activation energy, what's going to happen to the rate constant? So let me draw it out too. It's easier to visualize. So this thing can be rewritten as K equals A Awesome. So if I increase this, so EA is the activation energy. If I increase this thing, what's going to happen to this overall thing?
The rate constant's gonna get smaller.
Exactly. So if our activation energy increases, so what is activation energy? I'll give you. So
Is it the, I might be wrong, but is it the amount of energy needed for the reactants to change into products?
yeah, so it's so
Um,
when you
would
have
be
a
the
free
energy
diagram-
to, sorry.
Yeah, so it's this is called a transition state. So this is your reactants, this is your products, and this is your transition state. So when you're doing a reaction, there's an energy barrier that you have to overcome to reach your products. And that energy barrier is to reach the transition state. And this energy barrier to reach the transition state is called activation energy. Okay, so can someone tell me what activation energy is?
It's like the amount of energy needed for the reaction to progress.
Right. So the amount of energy for you to get to your transition state, so the reaction can progress. So think of it like if you're playing golf and you have to like if you have to like use a wedge to like get a golf ball up a hill, right? That's kind of what activation energy is. So the reaction can proceed. Okay. So we got that, right? And so we know that activation energy is in the denominator, right? So if your denominator gets bigger, like Newman said, your overall thing is going to get smaller. Okay. Does that make sense to everyone? Because we have activation energy in the denominator. We're raising E to the activation energy. So if we increase activation energy, this whole thing gets bigger in the denominator and the whole thing gets smaller. Does that make sense? Make sense? Okay. Awesome. So now we have something called oxidation state. So every element has something called an oxidation state. So usually you can just look at an element's charge and kind of figure out what its oxidation state is. Usually it's the same thing, but in some cases it's not. So on the MCAT, they always usually give you a compound with oxygen in it. And you need to know oxygen always has a -2 oxidation state. Nearly always. And hydrogens usually have a +1. So the oxidation states of the elements add up to give the overall compound's charge. So if I gave you water, for example, what is the charge of water?
Neutral.
Exactly. So if I tell you oxygen has a -2 oxidation state, and hydrogen has a +1, why does that add up to 0? So why is it neutral based on oxidation states?
So since we have two hydrogens and the oxidation number is +1, you just multiply that by 2, so it'd be +2. Since we know the oxidation number for oxygen is -2, you just add those two together and it just comes out as 0.
Exactly. Yeah. So that is correct. And that's basically what you need to know for the MCAT. Let's see. Let's go back to this slide, I think. Okay. So can someone kind of like explain this thing right here? Like why we use these terms to describe product rate? Like what do they actually mean? So this is related to this graph. So just like in your own words, like give it your best shot at kind of explaining that. So think of this as the A plus 2B is the red line. The blue line is X plus 2Y, the reactants. So why do we use these terms to describe the reaction rate? Like where do those come from?
So like as the reactants are consumed, the inverse is kind of the inverse rate is kind of true for the products. Like
Exactly.
they change inversely.
Right. So we measure our product rate as the formation of A, because A has a coefficient of 1. So the product with the coefficient of 1 is how you measure your reaction rate. All right. So that's why change over T, change in A over T is our reaction rate. We know change in A over T, like Krishal said, is the inverse of change in X over T. Because for every X that is consumed, an A is made. Okay, and we know that for every A that is made, 2 B's are made. So the reaction rate, which is, remember we're measuring A, is always going to be half of B, because there's half of A compared to B. Okay, same thing over here. For every X that we consume 2Y. So the change in X is always going to be half that of Y. Okay. And remember, we said the negative change of X is the change in A, which is our reaction rate. So that's why you can use all these terms to describe reaction rate. Awesome. Okay. So let's actually get to the questions now. So let's start out with the physics one. Can someone read the first paragraph?
I got it. There are different forms of frictional forces that occur. When friction acts on an object that is at rest, we refer to the frictional force as static friction. An object that is in motion is subject to kinetic or dynamic friction. Friction is a resistive force, one that dampens motion in dynamic systems and prevents movement in static systems. Friction occurs because an object interacts with either the surface it lays upon, the medium it is contained in, or both. Only objects contained within a complete vacuum are completely free of friction. A special case of friction is rolling friction, which is the friction experienced by a wheel that is rolling without slipping. There are no dissipative forces on the wheel subject to rolling friction because the wheel does not slip at the point of contact during the motion of the wheel.
Okay. And someone could read the second paragraph.
Researchers wanted to verify the coefficients of kinetic and static friction between various objects on various surfaces. A mass was placed on an inclined plate made of different materials, which was then rotated until the mass would slide down the incline. An IR receiver detected the first instant of the mass's motion. The coefficients of static and kinetic friction were determined and are shown in Table 1.
Okay, so can someone describe what the first paragraph is kind of talking about?
I think the first paragraph is basically summarizing what you were talking about, the difference between kinetic and static friction.
Right. And so is rolling friction static or kinetic friction? It talks about it over here.
Static.
It is static.
Yeah, static. Because the wheel doesn't slip at the point of contact. So that means there's no relative movement between the wheel and the surface. It's static. Okay. So here, basically what they're saying is they measured the coefficients of kinetic and static friction between various objects on various surfaces. So for example, here you have a steel object on a steel surface. The coefficient of static and kinetic friction is going to depend on the properties of the object and the surface. So one thing to know for the MCAT, coefficients are always dependent on the properties of the surface or the object. That's the only thing it's dependent on. It doesn't depend on anything else. So a lot of times they'll throw out like bogus answers at you, like the surface area impacts the frictional force. That's just wrong. So it's only the properties of the surface and the object that determines coefficient of friction. All right. So let's go to question 1. Okay, can someone read question 1 for me?
A 0.5 kilogram rubber block slides 2 meters down a 30-degree incline composed of concrete. How much work is done by the force of friction on the rubber block during the object's motion?
Awesome. So let's draw this out. Okay. Okay, so what are the forces acting on the block?
Gravity, normal force, and friction.
Exactly. So gravity, where's it acting? Like what direction?
Down.
Exactly, straight down. Where's normal force acting?
Perpendicular to the slope.
Exactly. And where is friction acting?
Parallel to the slope, going towards in the direction of its movement. Or no, away.
Exactly, yeah. So the main force we want to focus on is our frictional force. So let's call this FR. But how did we say we could calculate frictional force? What's the formula we use?
U times F. Mu times F.
So it's mu. So what is the F? Like, so so you got that right. It's mu times, but what force do we multiply it by?
It's normal force, right?
Yeah, normal force, exactly.
The Y component. Or sorry, the X component of normal force.
So this would be the perpendicular component. So when you're on a ramp, you want to say use perpendicular or parallel. So this is perpendicular, right? Because we said gravity has a perpendicular component and a parallel component. Okay. So normal force is which component again?
The perpendicular one?
Perpendicular, all right. And what's our perpendicular component at gravity? What do we use to find that?
mg cosine theta.
Exactly. So so the block is sliding on the ramp, right? So what coefficient do we use? Do we use static or kinetic?
Kinetic.
Kinetic, exactly. Okay, so where do we figure out our coefficient of kinetic friction? Can we figure it out from the problem?
It would be in the table that they gave us.
Exactly, yeah. So that's an example of just like looking back to the passage for important information, like the table, for example. So tables are usually important in the MCAT for getting like values that you need to use to solve the problem. So what coefficient do we use based on the question?
0.8.
0.8, right? Exactly, because we have a rubber block and then it's lining on concrete. So we like rubber on concrete. So we have 0.8. So we have 0.8 times mg cosine mg. So what is our m? What's the mass of the block?
0.5 kilos.
Okay, 0.5 kilos. And what is our gravitational constant? What did I say that was equal to usually?
10.
Yeah, around 10. And Is it sine or cosine that we're using?
Cosine.
Cosine, okay. And what's our angle?
30.
30, exactly, okay. So we have 0.8 times 0.5 times 10. So 0.5 times 10, what is that about? Oh, what is that?
5.
5, okay. 5 times 0.8, what is that?
4.
Okay, we have 4 times cosine theta. So cosine of theta, what does it say it is in the description?
0.87.
Okay, so our answer is going to be approximately somewhere around the high 3s, right? So let's just say like that's like 3.7-ish or something like that. Okay. So we know it's the high 3s because on the MCAT you don't get any calculator, so you kind of have to use approximations a little bit. So let's just say it's around the high 3s because 0.87 times 4, that's like around high 3s, I would say. So we got the frictional force, right? But what does the question ask for?
Work.
Work. So what is work?
Force times distance.
Okay. So we got our force. What distance does the force act through?
2 meters.
2. Okay. So we do 3, let's say approximately 3.7 times 2. Okay, which answer choice is closest to that? Okay, we'll think about negative in a second, but out of A and B or C and D, which one's closer to our answer?
C and D.
Exactly, C and D. So it's probably not around 3.7, it's probably around more like 3.4. So it was around 3.4 times 2, that's around 6.8. So let's say, okay, we get 6.8. Now, how do we figure out the sign? So you got to think about this conceptually. So does friction dissipate energy or add energy to an object? Remember, it's opposing motion. So is it removing energy or adding energy to the object?
Removing.
Removing, exactly. So is our sign going to be positive or negative?
Negative.
Exactly. Sorry, answer is negative 6.8 joules. And that is correct. Awesome.
Can you explain if you don't mind,
Yeah.
can you explain why in order to calculate friction we're using the cosine?
So okay, so we have our incline right here, right? We have our block on the incline. So we know that gravity always acts straight down. Okay.
Yep.
So gravity always has 2 components to it when on an incline. It has a perpendicular component to the block, which is this one. And it also has a parallel component to the block, which is this. Okay. So when you learn about like sine and cosine and trig, you kind of learn it like this, right? You learn this is you learn this horizontal part is your cosine, right? And you learn that the vertical part is your sine, right? Does that make sense?
Yep.
Okay, so we're on that page. Okay. So you want to think about like this. And you want to think about it like so you want to know that you want to think of like, imagine you have it like this and you just like flip it. So that's kind of hard to imagine, but if you just know your cosine is always going to be your perpendicular. So just imagine this part as the horizontal part of the circle and imagine this part as the vertical part of the circle.
Okay.
So let me actually draw a better circle.
If the parallel part of gravity is opposite in direction to the friction, why wouldn't we be using that one?
Okay, so because it asks the question asks how much work is done by the force of friction, right? So for the formula for friction, which is what I think it's just a given, is that the coefficient of friction times the normal force. So that's just like a physics derived formula that they gave us. That like I don't really know the explanation for that, but it's just a formula they gave us. So, and we know normal force is always perpendicular.
All
And we
right.
know the perpendicular component of gravity is always cosine of theta. So imagine this is the horizontal, and this is the vertical.
Okay. All right.
But in this,
I mean, it makes more sense now that if friction's being defined in terms of normal, why it would be the perpendicular component of the gravity.
well, so friction is parallel, but we use the perpendicular component to
Mhm.
calculate it because that's just the formula that physicists came up with.
All right.
Right? So friction is always parallel, and parallel is always sine. Okay. Yeah.
Wait, so we do use sine.
So okay, so you don't use because you use the perpendicular force to calculate the parallel force. So that's kind of confusing, I guess. So your frictional force is always parallel. And gravity also has a parallel component.
Yeah.
So your gravity going this way, that is calculated using mg sine theta.
Yep.
Okay. And then you have a frictional force opposing it, right?
Yes.
But how do we know how much our frictional force is? We don't. So that's why they came up with a formula to calculate it. And in that formula, you multiply your coefficient times your normal force, which is perpendicular. So even though friction is a parallel force, we're using the perpendicular force to calculate it. And why we do that is because that's just the formula that people came up with.
Just one more question. If
Mhm.
if we were to take would negative mg sine theta not be equal and opposite to friction?
So it's not equal to friction, because if it was equal to friction, then you just if it was equal to friction, the block would just stop moving.
Oh, okay.
Because okay, so yeah, that's a really good question, because the reason why the block is moving in the first place is because this force of gravity is bigger than the force of friction. Because static friction, it's equal, right?
Mm,
So
that makes
static friction is always equal to usually gravity. That's why it's staying still. But when you start moving, that's because the force of gravity is bigger than the force of friction.
okay.
Okay. Yeah. Yeah.
Could you is it I'm just trying to conceptualize the
Yeah.
if is it possible to break down the normal force into a parallel force also? Because I'm trying to define the actually this is probably like off the question now at this point. I don't want to take up time.
No, it's fine. You go.
I'm just trying to conceptualize the friction in terms of like the sum of the normal force and the gravity force, like what components of each of them would be required to calculate the friction force. Because right now it's like it's the parallel part of the gravity plus I'm assuming some component of the normal force.
So for friction, all you need to use is just this formula.
Mhm. Yep.
So that's the only thing you need to use.
Makes sense now.
And
Yeah.
the only reason why we even consider normal force in the first place is because it's in the formula. And we get normal force just by using the perpendicular component, which is mg cosine theta. So that's why we used it in the question.
Okay.
Awesome. Yeah, and then yeah, if you have any other questions, we can always do it after too. Awesome. Okay, next question. Okay, the kinetic energy of a block during testing comes from what? Does anyone have any ideas?
The work done by gravity?
Yeah, that is the answer. And could you kind of explain how you got to that?
Because gravity gives it like the parallel component that causes it to accelerate downwards.
Exactly. Yeah. So when you're doing this type of problem, you want to think it more in like conservation of energy. So potential energy always equals kinetic energy. Okay. So when you have a block sitting on top of a ramp, it has a ton of potential energy. When it slides down the ramp, all the potential energy is converted to kinetic energy. And so, like Andy said, that's right. The kinetic energy is coming from the force of gravity acting on the block. So like the parallel component right here. It's pushing, so it's pushing the block down and it's giving it kinetic energy. So how we can eliminate the other ones is, what did we say friction does? Does it remove or add energy?
Move.
Remove. So does it make sense that the kinetic energy of a block could come from friction if friction is removing energy?
No, it doesn't.
Yeah, so we cancel out that one. The work done by the incline. Well, the incline really isn't doing any work. The incline is just an object, right? It's not a force. So we can eliminate that. And there is no potential energy stored in the incline. It's stored in the block. So we can eliminate that. Does that make sense? Okay. If it doesn't make sense, feel free to speak up. Okay, let's move on to our next question. Since we're kind of running a little short on time, we can just do the physics passage today, and we can save the chem passage maybe for another day. Awesome. So number 3. So it says a second procedure was designed using a 2-block system connected by a string. At the instant before the system begins moving, which of the following is true? Does anyone have an idea of how we could start to solve this?
I mean, I would say just drawing the free body diagrams for both the equations first off.
Yeah, exactly. So this block is falling due to gravity. Well, it's supposed to fall due to gravity. But what's holding it up?
Tension.
Tension, exactly. Tension, okay. And so this block is pulling on the string. And the string is pulling on the block. So what is pulling on the block?
Tension.
Exactly. So this is the same force.
And would that be opposed by friction also?
Exactly, yeah. So the reason why the block isn't just sliding off the table is because of friction. Okay, and so these are all the forces we really need to look at for this question. Okay, so they're asking us which equation is true. Okay, so for block 2, what 2 forces have to be equal for block 2 to stay still?
Gravity and tension.
Exactly. So we say tension equals weight. Okay. So we know tension is equal to the weight of block 2. So, okay, but we know tension is also equal to the friction, right? Because how could this block be staying still parallel, right? How could this block be staying still if tension is not equal to friction? So it has to be equal. So we know tension is equal to friction. What's our formula for friction again?
Coefficient of friction times normal force.
Exactly. So if it's staying still, what coefficient do we use?
Static friction.
Exactly. Normal force. Awesome. So, and what block is it the normal force of?
Block 1.
Block 1. Okay. And so we know the friction force. The friction force is equal to the tension, right? We know tension is equal to the weight of block 2, right? So we can write weight of block 2 equals coefficient of friction times the normal force of block 1. So what answer choice is that?
A.
A. Awesome. Does that make sense to everyone? If it doesn't make sense, just we can go through it. There's no rush. Awesome. Awesome. Okay, so that looks like it's correct. Almost done. So which of the following is true regarding the effects of rolling friction on an ideal wheel? So take a second to look at the answer choices and what could it be? So how do we say whether we determine kinetic or static friction? What was the thing we look at?
Motion at like the point of contact.
Exactly. So does a wheel have motion at the point of contact?
No, so it is static friction.
Yeah, so what would the choice answer be?
C.
Awesome. Anyone have any questions about that? Okay. Last question of the day. So again, we have our block. And we're pushing on it. So let's say we're pushing on it, call this P, and then it has friction opposing it. So based on how did we say friction works? So we said friction works like this. Right? That's how friction works. So you build all the way up to static friction, and then you drop down to kinetic friction. So if the frictional force increases all the way up until a maximum, how is the force that we need to push it gonna be affected if our static friction just keeps increasing? If something's resisting more, what happens to the force that you need to push on it?
Increases as well.
Right. And eventually your hand can push as long as you want to, right? But friction can only go up to a certain point, right? So friction has to peak at some point. So let's look for a graph that has a peak somewhere. This one is wrong, right? Because friction just goes, it just keeps increasing. Whereas, so we can eliminate A. C, okay, it stops peaking. D, it stops peaking. But C, it says it increases and then just becomes constant, right? That's not what we learned here. We learned that it increases, then drops down a little bit. Okay. So you keep pushing on the block. The floor keeps providing more friction until it gets to a maximum point. Then the friction is going to drop down to it's going to drop down to kinetic friction, at which point you will need less force to push the block. So what graph would be correct then? So we have an initial buildup, it peaks and then drops down. What graph shows that?
D.
D. Okay. Awesome. Does anyone have any questions on that? Yeah, so I know today was probably a bit more confusing than the bio passages. That's generally kind of characteristic of physics for most people, at least. And I know this is our first time doing physics too, so. So how would you improve upon today's session? Or-
I think it was good the way it was. Maybe, I don't know if this is just because I'm like I need like proofs behind like my like physics formulas and stuff, but like I'm trying to figure out the mu n right now. But
Right.
that's
You could probably, if you look it up online, I'm sure they have a proof, but
yeah.
I personally don't even know how to come up with that formula. That'd be pretty tough, but I'm sure online they could probably have that. So yeah. Anyone else have any feedback? Awesome. So if not, then everyone's good to go. Oh wait, let me stop sharing. All right, and I guess I'll see you next week, because we have sessions every Monday now, so be consistent. Yeah. All right, see you guys.
Okay, thank you, sir.
No problem.